Things are good. Great. So quiet. Couple of things before we get started into some new stuff. First, you remember your major assignment is due on Tuesday. Part of that, again, is being able to plot parametrically, and I sent that parametric plot function to you. What I would do when you're trying to plot it parametrically, first I would run just that little snippet of code so it's stored into the memory before you actually run your cubic spline code. The second thing is make sure that in that parametric plot code that I sent you, I assume you're going to want to plot the points that you've generated and then run the splines through it. If you leave that, there's, let me just pull up the code. Instead of me just yakking about it. This piece of code right here, this line, the one that says plot, remember that opens up a blank plot window, so then it'll draw, and then the lines command draws in the actual parametric part. You don't want to put in that, you want to delete this line out, this plot line out, because you're going to want to put in each little piece of your spline in between the points. If you leave that plot command in there, it's going to erase everything every single time. So the first thing you'll want to do is plot the points that you have for your signature. That'll open up a plot window. And then if you call this function without this plot line in it, it'll add in the pieces as you go. So I want to make sure I mention that you want to delete that plot line out of there when you call that particular function. Okay. Or comment it out, either or. Just make sure it doesn't run. That particular line doesn't run. Because otherwise, all it'll do is going to write over the top of every single graph it does. And then all you'll get is your very, very last piece at the end. It's not very interesting. So if you want to, you can do it a couple of ways. If you want to run your splines with the points in there, that's fine. But if you'd like to see your signature without the points in there, just instead of telling at the very first thing, telling the R to plot the points that you created for your signature, just run that particular line outside of the parametric plot function. It'll open up a blank plot window, and then it should draw in your signature without the points. And you should be able to see your signature there. So I just want to make sure I mention that. So that particular line here, if I can get to it, that particular line there, you want that to not be there. Okay. Again, otherwise it will just rewrite over the top of itself over and over again, which is not very interesting. Depending on how many points you use for your signature, when you put them in GeoGebra, depending on how many points you use, it'll take it. That'll be it. The more points you use, the longer it'll take for your code to run. Okay. But other than that. So I just wanted to mention that. Other than that, as far as your homework went, so I gave you those 3 problems on there. One was to create the quadratic spline from the formulas that we came up with. One was to create the cubic spline from the Excel code that we had, or the Excel sheet that we had. That's the only part. Oh, there's somebody coming in. That's the only part that's going to be on there. Sorry, that's the only time that you're going to be asked about those particular things. However, the second question where I asked you to verify that something was a cubic spline, that would be fair game for an exam later. Okay. So if you're thinking about preparing for exam later, which we'll have one in a couple of weeks, well, whenever we get to it, before the end of the semester, that second problem on there with verifying that something is a cubic spline, or being able to go through and say why something isn't a cubic spline, that one of the conditions isn't met, that will be something that will be on today.
Would the next exam also be comprehensive of stuff you've already had?
No. Okay. No, it'll be splines. We're going to do start least squares today. we're going to talk about Fourier series, and we're going to talk about Monte Carlo methods for doing different simulation types of things, and then that's all we're going to do. So that's where we're headed for the rest of the semester. But no, there won't be anything that's comprehensive. Unless you want it today.
I'm good.
Now, as far as the last major assignment deal have, there'll be pieces of old stuff, but there won't be anything that's attested on, per se, as an in-class test. What's that? Bring the pain. All right. Well, let's start talking about some new stuff, which talks about least squares approximations. The goal today is to set things up in a couple of different ways and do some calculations. And then on Tuesday, we will go through and talk about how we can determine how good an approximation is, and then also talk about how we can generate some of these particular things in R. But so my goal again for today is to get things set up and then be able to do the computations through Excel in particular. We'll probably also use GeoGebra a little bit just because it's easier to see some graphical things in GeoGebra than it is in Excel. And then, like I mentioned, on Tuesday, we'll talk about how we can check to see how good of an approximation the least squares model is. And then again, be able to do some of those computations through Excel, and then also be able to run it in R and have R verify what we're getting. Okay, so that's the next 2 class periods, basically, what we'll do. This least squares approximation also will extend into the Fourier series stuff. So Fourier series are actually least squares approximations. Okay, and then we'll talk about what we mean by that when we get to it. All right. So the idea here is that we'll start very simply. If we have a set of data, whatever that set of data happens to be, let's say we have some x's and some y's and we plot some points. Certainly, if I just take some points and just throw them up in a plane, probably not all of them fall on the same line. Right? I threw, what did I put, 6 points up there? Probably not very likely that those 6 points are all going to be on the same line. But the idea here is can we find a line that in some sense approximates this as best as possible? So we're looking for some line going through here that's the best possible line that we can get in some sense. So we'll talk a little bit here about what we mean by best possible line. But this is the idea behind least squares. I don't have a perfect line that all my points are. Try that again. The points don't all fall perfectly on the same line. But I would like one line to give me an approximation of what's going on. This is a switch in what we've done so far this semester, right? So far this semester, we have tried to make something go through each of those points, right? Either we took a single polynomial and ran them all the way through all those points, or what we did in the last couple of weeks is, okay, we picked a piece here, and then pick a piece here, and then pick a piece there, and pick a piece there, pick a piece there, and put them all together, right? In some fashion. So this is a diversion from that, right? A departure from that idea. Okay. All right. So we know that if we have a line, this is going to be something with a constant and then something times an x value. This is the line, right? But there's going to be some sort of an error piece in there as well that we need to figure out what's going on. So if I have a line here, there's also going to be some error associated depending on where that x is, right? That error is going to change depending on what x value we're in, but that's the idea here. We're going to have some error. So what I mean by this is that if I plug in if I plug in this particular x coordinate at this point, this would be the approximation here on this line, right? So then the error would be that little bit, right? Now that's associated with a particular x value. Those errors are going to change as you go along, right? There'll be an error here, there'll be an error here, one there, right? Those all depend. I mean, writing epsilon every single time, I don't really mean a single epsilon. I mean an epsilon for that particular x value that's been plugged in. I just didn't want to put a whole bunch of extra subscripts in there. Okay. What we want to do is that we want to make all of those epsilon pieces as small as we possibly can. All right? I mean, there's lots of lines that we could say approximate this particular thing. One thing that you might use, if you wanted a constant function that approximated this data, is probably a very easy one that you would probably use. If you said, if I gave you a set of data and I said, use a constant function, a single constant that approximates the data, what constant would you probably choose to do that? Would I use one that's up here? No. Would I use one that's down here? Or would you use one instead? Oh, yeah. And in the middle of the word I was looking for, and somebody else said average. Exactly, right? You'd use the mean, wouldn't you? If I said use a single point to do it, we would use the mean, right? And there's a reason why I wanted to discuss that, because that piece is actually going to pop out of this here when we go through the computations. Okay. But yeah, if you were to use a single value and said, I'm only going to allow you one choice, what choice would you use? You'd pick the mean, right? That's probably your best guess. So pick something in the middle, right? You pick the mean. All right. In some sense, however, we want to not in some sense. We actually want to use a line that slopes to make it a little bit better than just using a single point. So the idea here is that I want to make these errors as small as I possibly can, right? Certainly, if I start drawing some other things in here, if I take a line that's really, really slanted, those errors get bigger, right? All right, we agree with that. So I want to make sure that somehow these errors get small. So if I add up all the errors, I would want the adding up of all of those errors to be as small as possible, right? But notice that some of your errors are too big, right? I've got my line value is above this point. Some of my errors are too small. My line value is below this point, right? And it turns out that if you get your line of best fit and add all of these errors together with the positives and the negatives in there, you're always going to get 0. Okay? So I don't want all the errors to be, I don't want the errors to keep their signs. If I have their errors keep their signs, when I add them all up, I'll end up with 0. Okay? We call that the deviations from the mean, for example. So again, you figure that the mean is going to be in here somehow. So let me show you what I mean by this. If you have a set of data, say you have x1, x2, x3 out to xn, and then we use x bar to denote the mean, well, we calculate the mean by doing, of course, the sum of the x's and then divide by how many there are, right? Okay. So if I do all of the deviations from the mean. So what I mean by deviation is that if I take the data point and subtract off the mean and add them all, that's a deviation. So this is how far the data point is from the mean. Okay, that's what I mean by deviation. If we add up all of these deviations, well, what do we get? Well, we know that summations break up just fine over subtractions, right? There's no issues there. Okay. But for a given set of data, we have just one mean, right? Agree? Okay. For a given set of data, we have just one mean, so this is a constant. If I add a constant to itself n times, what do I get? That constant times n, right? So this is just n times the mean, right? But how did we calculate the mean? Yeah, add them up and divide by n, right? So what does n times x bar equal? The standard deviation of the x of i's, right? So what do we end up with when we're done? 0. So again, if we add up all of the deviations, anytime you add up all the deviations over the entire data set, you always get 0. So this is not a good way to try to figure out a measure of error. And if you've done anything with standard deviation or variance in the past, this is not what you want to do. Okay? The reason why is if I do that deviation, it includes the positives, it includes the negatives, and they end up all just canceling themselves all out. Okay? So I don't want to make, the moral of the story here is that I don't want some of my errors to be positive and some of my errors to be negatives. I don't want displacement, right? From a physics perspective, that would be a displacement, right? Keeping the sign on there. I want distance. I want positive errors. Okay? Now, there's two natural ways that you could make positive errors. One, from an algebra perspective, take absolute value, right? And there are some instances where you do absolute deviations with absolute value. The problem is here that, think about what we're trying to do. I want to make the error as small as possible. I want to find the minimum error in some sense. From a calculus perspective, how do you find minimums? Minima. Take a derivative, right? Do derivatives behave nicely with absolute value? No. The absolute value tends to have sharp corners in it, right? So we don't want to do absolute value if I'm trying to minimize something and then trying to get a handle on how to find that minimum in a calculus fashion, right? I don't want to try to figure out where all those sharp corners are, okay? Instead of making a positive number by taking the absolute value, we'll make a positive number by doing what other operation makes it positive? Squaring it, yeah. We'll take the square of it. So that's why we call it least squares, okay? So what we're going to do is we're going to take all the squares of the errors, right? So we want to minimize the sum of the squared errors. So we want to, if we have all of these errors, this time I will put a subscript in there. We'll have all of these errors, we will square them and add them up. We want to minimize the sum of all those errors. Okay, that's the idea. This is where the name least squares comes from. You're taking the squares of the errors and trying to minimize it. That's why we call it least squares. All right. So let's think about a way we can do these errors. Again, the error is the difference between what the actual y value is and what the predicted y value is, right? Okay. So this would be I equals 1 to n. Y sub I is your actual y value. I'll write it as an A. Some books use alphas. Oops. I want my A to be my constant. So my predicted y value would be what I get when I plug in x sub I into the line, right? So I get, that would be A plus bx sub I. I'm subtracting it, so that's why I've got minus signs in both places. My error then would be the difference between predicted and observed over a square. Bless you. Okay. All right. So this is the expression that we want to minimize, and I want to figure out the A and the B that I want, right? Okay. So this is a function of two variables. I'll call it S just because I'm doing a sum and I'm squaring. So S seems like a natural letter to use. Don't worry about what the letter is. It doesn't matter. Okay. But I have a function of two variables. Remember, the x's and the y's are given to you. We're trying to find the a and the b. So I have a function of two variables that we want to find the minimum of. So now I needed to use some calc 2 or calc 3 ideas here to do that, right? So let's think about what a picture would look like. Remember, if you graph a function of two variables, you get a surface. You have to graph it in 3 dimensions, right? So if you're looking for an extreme value, I'm going to draw a bump because it's about all I can draw. Right? If I'm looking for an extreme value, I'm looking for the top of a hill or bottom of a valley. We're doing minimum, so I'm really looking for the bottom of a valley, but I didn't feel like drawing the bump the other way. Okay? All right. So notice that, though, from a calculus perspective in 2 dimensions, if I think about it in my x direction, it needs to top out in the x direction. In my y direction, it also needs to top out in the y direction. Correct? Right? So remember, the x direction would be your partial with respect to x, right? And your y direction would be your partial with respect to y. So we need to solve the system of the partial of s with respect to a is 0 and the partial of s with respect to b is 0. I needed 0 in both directions, right? I need to make sure that I have a critical number with respect to x, a critical number with respect to y, but in this case, my x and my y are my a and b, right? So this is a system that we need to solve. To help out the algebra a little bit, we're going to change our function slightly. We're going to shift it just so that it makes our algebra life a little bit nicer. Okay. So rather than writing my function just as a minus b x sub I, let's shift it a little bit and make our function, oops, I'm going to call it, I'm going to use an alpha or an a hat and then a b hat times x sub I minus x bar. You know how we've done some shifting with the different functions that we've done with the splines and all those kinds of things? Doing the exact same thing here. So it changes my alpha or my a a little bit. I keep saying alpha because stuff we were reading, preparing for class had alphas rather than a's. It'll change our a because we're shifting, right? Okay, so that's why I'm using a hat over the top of it. In the b, well, it should be the same, but we'll write it as a b hat just to keep it consistent. Okay. All right. So this, I know I called the S the original thing. I'm going to abuse the notation and just call that my S now. All right. So let's take our partials. I want to differentiate with respect to A. Well, derivatives behave nicely with respect to sums, right? So that's not going to change anything. What am I going to have to use inside here when I take the derivative? I've got a thing squared, so what do I need to do when I take the derivative there? Chain rule. So I'll bring the 2 down in front. And since it's a constant, I can pop it all the way out in front of the sum, can't I? Right? And then I need to multiply by derivative of the inside. Which variable are we? Oh, I should use a hat. Sorry. I should put an a hat on these things. B hat. I'm differentiating with respect to a hat. So what's the derivative of the inside with respect to a hat? So if I differentiate the a, I get, you get a -1, right? Because the other terms pop out. This is going to be a 0 because there's no a's in it. This will be 0 because there's no a's in it, right? So we just get -1. How does it change when we do the partial with respect to b? What changes? Good. All right. So I took the derivatives. What do we want to do with each of these derivatives? Set it equal to 0, right? Okay. So let's look at the first one. I'll just pop the negative out in front as well. And -2 doing anything? Can we get rid of the -2? Yeah, just divide both sides by it. I still get 0 on the left-hand side, right? What are we trying to solve for? We're A and B, right? Let's solve this for A in particular. Okay? Start there. What would I want to do? I want to solve for the A hat. What do I want to do? Split the sum. Okay? Let's do that first before we do anything else. So we can divide out the -2. That's not doing anybody any good. But it literally doesn't matter because it's going to make it go away. Sum I equals 1 to n of y sub I minus sum I equals 1 to n a hat minus sum I equals 1 to n b hat x sub I minus x bar. All right. Each of these sums, what's changing? What are you actually doing when you take the sum? What changes? What value changes? So just in general, I mean, when you take a sum, I'm writing it this way, what actual changes? How do you do it? Well, so we're going to take a 1. The variable that actually changes when you're doing the sum is what? That's what I'm trying to ask. The I is what changes, right? So these values change when the i's change, but does this one? No. Does this one? No. These do, but this doesn't, right? Okay. So that second one, what do you get for the second sum?
Minus NA.
Good. Minus NA hat, right? That's all we get. In the third sum, what can you do with the B? It's a constant. What can you do with it? Take it out in front. Good. What do you have now for your sum? Yeah, this is going to be 0, right? Because it's the sum of the deviations. We just talked about that a little bit ago, didn't we? This term is 0. Okay. So now let's solve for your A hat. When I solve for A hat, I get 1 over n, sum from I equals 1 to n of y sub I. What's another name for that? Add up your y's and divide by how many there are. The average, yeah. Now, what did I ask you when we started this? I said, if you were to use a constant function to approximate the data as best as possible, what would you use? The mean. Notice that comes out here. Right? Okay. So now we can solve for B. Unfortunately, the B isn't quite as nice, but it's okay. So to figure out what the A is great. I mean, again, this is why we shifted things, right? Made this number come out a little bit nicer. Okay. The B one, I mean, it's a formula. We just want it to be as nice. So what did we have? We had 2 times. I'm going to pop the negative out in front. Oops, I still want to set this equal to 0. Pop the negative out in front. We had y sub I minus a hat minus b hat x sub I minus x bar, quantity squared times x sub I minus x bar. The only difference between the two was we had a -1 in the first one and a negative x sub I minus x bar in the second one. Right? But now we can solve for B.
It wouldn't still be squared.
Oh, you're right. It's not still squared. Yep. Thanks. And now we can plug in for the A and solve for the B, right? We agree with that? Rather than going through all of that algebra, your B, I'm just going to write down what it should be. This is why I didn't want to go through all the algebra. Okay. That's what your B will be. So again, the way these come out, pardon me, goodness. The way these come out, again, we shifted those things. So if you've seen some least squares regression formulas for your constant and your slope, you may have seen these formulas slightly differently, but the reason why is because we shifted things, right? But the reason why we shifted things is that we wanted to get this to where we could see what I want to do it for two reasons. One, the calculus is a little bit simpler to do, and certainly to solve the equations. But I wanted to see that when you do this least squares, this mean plays an important role. The mean of the y's plays an important role. All right. So this is, again, kind of doing the calculus idea for how we want to do this. But we're probably never going to calculate them this way. Okay, but I wanted to show you the calculus way and how you can get these ideas. All right, so let's switch gears a little bit and talk about a different way that we could possibly approach this from a linear algebra standpoint and see if we can come up with a similar kind of formula. And this will allow us to use the technology a little bit easier. In particular, it'll allow us to use Excel a little bit easier. Okay, all right, so to draw a different picture here, let's say, pardon me, I have, let's say I want to try to fit this to, let's say I want to do this in 2 dimensions. Let's say I do it in 3 dimensions with a 2-dimensional object rather than doing a line. It still works for lines, but at least the pictures will make a little bit more sense if I do this in 3 dimensions to show what we're talking about. All right, so if, say, I wanted to have some points that I wanted to approximate, let's talk about it this way. Try this. All right, let's start with some plane that I have. Okay. If I think about it from a vector perspective, in this plane, I've got lots of different vectors in here, right? That I could have. And it doesn't have to be a plane. It could be all sorts of different objects. But in 2 dimensions, you can kind of see all sorts of different vectors that we could have in here, right? Okay. But for a plane, and if you think about it just from what you do in, say, Calc 3 ideas or in physics ideas, if I have a plane, I can describe everything in a plane using just two vectors, right? In particular, if I think about, I have the vector here that's, say, 1, 0, and the vector here that's 0, 1, then a lot of times we call this what? I, call this J, right? And then I can write any x, y as x times I plus y times j, right? So I have 2 things that satisfy it, right? All right. Another way to think about this from a matrix perspective is that my vector I would be the 1.10, or the column 1, 0. My vector j would be the column 0, 1. And I could put my x and y here, right? So I could think about it as a matrix product. Remember how matrices get multiplied together? Take the row times the column, the row times the column. Talk a little bit about that as well, right? Okay. So in particular, just to use some linear algebra language, this is a linear combination of the I and j. Linear combination just means we're doing a constant times a vector plus a constant times another vector, and so on down the line. Okay? This is a linear combination of I and j. If I make those into columns here, I get a linear, when I do this product, I get a linear combination of the columns. This column was your I column. This column was your j column. And if you put those together, you would have a linear, you'd have your x times your I column, right? You'd have x times 1, 0, and your y times your 0, 1. Okay. All right. So from a linear algebra perspective, when I'm talking about doing this kind of a plane idea, this turns out to be the set of all vectors of the form a matrix times some vector. Okay? Where my matrix here, or these vectors here, are those, these are kind of your generating vectors. I'll call it generating vectors. It's called a basis for those of you who've had or are in linear algebra. It's a basis. These are generating vectors for your, in this case, I'll say plane, but whatever space we're talking about. All right. Anyway, long story short, I can represent this as a matrix multiplication, okay? Just like I did over here, okay? That's the idea. All right. Say I have some other random vector that goes this way. Say I have some other random vector that goes up that way. If I think again my three-dimensional picture, if I have a vector that comes off my plane up, can I write it as a times x equals that? No. Okay. So this one in linear algebra speak, we would, if we tried to set ax equals b, we would get what's referred to as an inconsistent system. You can't solve it. Okay. But what I want to try to do is get the best possible approximation I can. Okay? I want to try to get this as good as I can get. Okay? Well, if I want to get this as good as I can get, I want to have some vector down in my plane that best approximates. Think about it as a shadow, right? That makes sense? Okay? So if I want the best thing that approximates it, this is kind of a shadow. Notice in this case, I would have another vector going this way, up, right? I'd have a difference between those two. Notice in this case, this would be your error, right? This is the kind of the least squares error idea. This length of this vector would be the error that's between my approximation of the best I can do is some vector that's down in my plane. There is the distance between the endpoint of that vector and the endpoint of the thing that I'm trying to approximate. I want to try to make this as small as I possibly can. Well, what's probably going to be true, I'm not going to go through why it has to be true, but what's probably going to be true about these two vectors if I'm going to make this one as small as I possibly can? What better be true about this vector here and this vector here? What better they be? Perpendicular if I'm going to make that as small as possible, right? Think about it from a Pythagorean theorem standpoint, right? If these aren't perpendicular to each other, then it's not going to be, the thing's going to be longer this way because you can make the right triangle, make that the hypotenuse, right? Okay. So what our goal here is that we want to make that ax minus b vector as small as possible. Okay. Remember when you subtract vectors, I've got this would be your ax. Remember, anything that's in there could be written as that a times the x, right? This is my b vector, then this would be the difference between those two. Actually, I guess it would point the other way, the way I have it written, but it doesn't matter. I'm talking about length, right? So I want to make that length as small as possible. But again, it's hard to make it as small as possible as far as length goes. Well, that's not true. I can make this as small as possible to make its length as small as possible. I can also make the square of it, the square of the length as small as possible. Is the same idea. So I still have length squares as far as length goes here. All right. This shadow vector that we called down here, the shadow, we refer to this as the projection of B onto that space. Okay. Now, it is possible to compute that directly, but we're going to be a little bit clever and not do it directly. Okay. The let me just I'm going to give this space a name. I'm going to call it W just so I can refer to it. All right. So we want to solve this system. Okay. I want to solve this matrix equation. So my AX is it's a vector that's down in my space, my W. This is just our notation for the projection of B onto the space. So that's why I called it a W. Yeah, just give it a name. Doesn't matter what the name is. Okay. We want to solve this system because that's the best possible approximation. Now again, there are ways that you can find that projection directly. Okay. We don't want to do that. Okay. We're going to be clever. We like being clever. So to be clever, we're going to take B minus both sides here. Now let's look at that vector on the right-hand side of the equation. Going back up to my picture, my wonderful picture up here at the top. Your B is going this way. Your projection is this thing down here, right? Agree with that? Okay. So this vector here, the one that's up and down, would be the B minus the projection. It's perpendicular to everything. It's perpendicular to W. It's perpendicular to everything in W. Okay. Pardon me. That vector there is perpendicular to absolutely everything in W. Okay, so for those of you who have dealt with vectors in particular and dealt with dot products, how do you check if two vectors are perpendicular to each other in terms of a dot product? What do? Yeah, you take the dot product of them and get 0, right? So remember how you do dot products for vectors that are in Euclidean space. I'll just do it for two vectors. So for example, if I had 3, 5, and I want to do the dot product of, say, -10, 6. Remember, you do your dot product as first two things multiplied together plus second two things multiplied together. Right? In that case, we get 0. So those things would be perpendicular. Okay? So we can check with dot product. Pardon me. All right. So again, this has to be perpendicular to absolutely everything in W, right? So remember again, your A here is made up of columns that generate everything, right? Correct? We agree with that? Okay. All right. If a vector is going to be perpendicular to everything in W, then it's going to need to be perpendicular to all of these columns because these columns are in W, right? If it's going to be perpendicular to everything in W, then it's going to be perpendicular to all of those columns. right? Okay. We can check perpendicularity by doing dot product again. So I would need to do the dot product of this with all of these columns. Well, that's harder to write as a matrix equation. I'd like to multiply both sides by the same matrix, correct? Okay. Well, let's think about how the product would go. Do this off to the side. So I've got my B, say this is my, I'll just write them as Z's, doesn't matter. All right? That would be what my, I'm just using this to notate this particular vector, right? I want to do my first, whatever column it is, I want to do my first column, say, and I want to do the dot product. If I wanted to recognize this as a matrix product instead, would I want to write it this way? Would I want to write it that way as a matrix product? Does that work? No. What would I need to do with this instead? Write it as a row. How do I change what matrix operation changes columns into rows? Transpose, right? So I can do a dot product by doing the transpose of this times that vector. Okay? That's how I can do a dot product. And this is a way actually to define the dot product in terms of matrices. You can do it as a matrix multiplication. You take the two vectors and you transpose the first one and multiply by the second one, if you think of them as columns. Okay? All right. I want to do that for every single thing in my space. Well, again, I need to take each of these columns and multiply and do the dot product with this thing and get 0. Well, if I want to do each of those and change columns into rows, I'm going to take the transpose of my entire matrix. Okay? So if I multiply both sides by A transpose, the right-hand side is the 0 vector. Because this B minus the projection of B onto W is perpendicular to every single column of A. We transpose A, so now we're doing dot product. So each of those entries is going to be 0. Okay. So now, if we rearrange this equation, we can rewrite this as A transpose A times X equals A transpose B. This gives us a system that we can actually solve. This is referred to, if you write out all the equations involved in this system, these are called the normal equations for the system. There's multiple equations in that one matrix equation. All right. That was a lot of work to get to that point. Okay. That's okay. We're almost home now, and then we can actually do some things with numbers. Sound good? Okay. All right. All right. So let's talk about what we have to do here. A is some matrix. A transpose has dimensions that are flipped. When I multiply these two things together, I get a square matrix. Right? Remembering how matrix multiplication works. To be able to solve for x here, it would be nice to be able to, well, if you think about it from an algebra perspective, with just algebraic equations, you'd like to be able to divide. We don't divide by matrices. What do you do instead? Multiply by the inverse, right? It'd be nice to have this be invertible, that I can take the inverse and multiply it on both sides and get the least squares solution. Good news is that as long as your system is not stupid, you'll be able to do that. And what do I mean by not stupid? Well, first remember that if we're doing least squares, think about back to my original picture. If you were to set up a system of equations with at least that line, notice I've got two unknowns, the A and the B, but I'd have 1, 2, 3, 4, 5, 6 equations. I'd have more points than I have parameters that I'm trying to solve for. Okay? So as long as you have more points than parameters, and you just gotta make sure it's not stupid, like they all fall on the same line, kind of thing, right? Just gotta make sure it's not dumb, and the things that you're gonna have are not dumb. As long as it's not stupid, it'll have a it'll be invertible, and you'll be good to go. Okay? All right. It's just say it as a linear algebra thing. You need to make sure that the matrix you start with has linearly independent columns. That's all you need to worry about. Okay. Good news is, for our purposes, nothing will ever be stupid. Okay? All right. So going back down here then to solve for x, you'll take the inverse of your A transpose A matrix and then multiply by A transpose and multiply by B. This gives you a least squares solution. The entries in your x here will be the parameters that you need. Okay? So let's talk about how we set up the system and then talk about what the solution has to look like. So let's do an example here. All right. Let's say we have, doesn't matter. Let's say that the data points that we have are 6.8 and 0.8. These aren't the greatest of numbers, but that's okay. 7 and 1.2. 7.1, 0.9. 7.2, 0.9. 7.4, 1.5. And let's say we want to fit this to a line. We want to find the least squares line. We'll do some other least squares ideas besides just lines, but let's do the least squares line. All right, so again, if we're doing a least squares line, I'm trying to fit this, correct? I want to figure out what the A is, what the B is. So when we plug in an X and get out a Y, we get an equation that involves A's and B's, right? Your first equation would be 0.8 equals A plus 6.8x, or B, sorry. Right? That would be your first one. The next one would be 1.2 equals A plus 7B, and so on down the line, right? Writing this with matrices, your matrix A then would be the coefficients of the A's, say, in your first column, and the coefficients of B's in the second column. Well, notice that when we've got a constant term on there, the coefficient on the A every single time is 1, isn't it? I just didn't write out the other three equations, but you get them the same way. But notice that every single equation is just going to have an A plus something, right? There's nothing multiplied by the A. What would be your coefficients on your B? The X value is good. 6.8, 7.0, 7.1, 7.2, 7.4. Okay. There's your A. Your B are your Y's. So your B would be 0.8, 1.2, 0.9, 0.9, 1.5. Now that we have those values, we can literally plug it into this formula and figure out the solution. Okay? So let's do this in a couple of different ways. I'm going to do it in Excel first, and then we'll do it in GeoGebra so you can actually kind of see the pictures as we go along. Okay? All right. Good news is that this is pretty straightforward in both of these things. Okay? All right, so go over to Excel, that I already have open. Let's zoom in a tad so we can see things. All right, so the first thing I'm going to do is I'm going to set up my A matrix. Okay, remember my A matrix has 5 1s down that first column, and the second column is 6.8, 7, 7.1, 7.2, and 7.4. Okay. That's the A, right? So remember what we need to compute. We have to do A transpose times A, do the inverse of that, multiply it by A transpose, and then multiply by the B, right? So I'm going to go ahead and put the B in next to this, and then we'll do all the work below it. You can set it up however you want, but the B was 0.8, 1.2, 0.9, 0.9, and 1.5. All right. Again, Excel's nice because if you start typing what the formula should be, it'll pop up for you. What do I want to do with the A first? Take the transpose, right? Start typing in transpose. Notice that's the first thing that pops up. I typed in TR. Transpose came up, right? Okay. I want to do the transpose, highlight the entire thing, or you can type it in. Of course you want. Oh, why are you? There we go. Why did you do that? Stop it. Okay. Highlight the entire thing. And of course it went over the top of this stupid thing again. You just hit enter and so I can go in there so you can see what it looks like. All right. Got it. Okay. Notice that Excel knows that it's not just supposed to have a single number output, it should have an entire matrix output, so it could look kind of weird, right? So it made it, it was originally 5 by 2 and now turned it into a 2 by 5. All right. What do we want to do with the A transpose in the A? Multiply them, right? So the command for that is mm molt. So it's molt. Okay. So it's matrix multiply, but molt. Okay. All right, so the A transpose goes in first. You can type in the range if you want to, or highlight. If you would to type in the range, it would go from A7 to E8. If you type it in directly if you want to. Either way works, it doesn't matter. Right? You can just drag and highlight over the top of it or type it in. Okay. Separate it with a comma. Your A matrix is A1 to B5. And notice that I'm putting a colon between them. So it knows that it's doing an array there. So again, A transpose is the stuff that's in from A7 to E8. The original A is from A1 to B5. Okay. So far so good. We should get a 2 by 2 when we're done, and we do. Okay. Okay, so remember you gotta put your second matrix in there too. So you gotta put a comma. You put a comma in, and then your original matrix. Yeah. So you gotta put both in there. There you go. Were you able to get that matrix? Yeah. Notice that this matrix is symmetric. What I mean by that is if I look at the main diagonal goes from upper left to lower right. The things that are off the diagonal should match. Okay. That matrix should always be symmetric when you're done. Okay. What do I want to do with this matrix now? What do I want to multiply it by? A transpose and then multiply by the B, right? So the next one will be matrix multiply this matrix that we just came up with and the A transpose matrix, which is down here. Oh, I got to take the, I do have to take the inverse of it first. Right, sorry. Oops, I messed up. Sorry. I got to do the inverse before we do the multiplication. Sorry. Good news is that the command for matrix inverse is minverse. It was mult, it's minverse. Okay, sorry. I do need the inverse of the matrix we just found. Thanks, Ian. Okay. There's the matrix inverse. Now I need to multiply this by the one we just found by the A transpose. The reason why it's putting the little hashtag in there is it knows that you've got what Excel refers to as an array function that we're using. So it's spitting out an array. It's called an array function. So it knows that it's the result of an array function, which is why it's showing the hashtag rather than showing the range of cells that you're highlighting. Because it knows that those other cells have been written over by an array function. That's why it looks weird. And then finally, at the very, very end, we're going to take this one we just found, maybe, and multiply it by your B, which is the original. So the negative 5.33 is your y-intercept. The way we set it up, right? This was constant, this was x term, right? Constant x coefficient. This is your y-intercept, this is your slope. So the equation of the line would be y equals negative 5.33 plus 0.9x.
Are we multiplying on this one? I think I missed it.
Oh. So this last one here?
Yes.
Okay, so you take the previous one, this one, and multiply it by your b's that are over here. Yep. So let's label a couple of things here. All right. So this was your A matrix. This was your B. This down here is A transpose. This is A transpose times A. This is A rather than me keep typing in transpose all the way. We'll use A superscripted with a T for the A transpose, A inverse. This is A transpose A inverse times A. And this finally is, I'm just going to type previous times B. So I have to keep typing the longer and longer things. So that's what each of those pieces is. Same process every single time. Doesn't matter what you're trying to fit, as long as you're trying to fit a linear model. Okay. By the way, what we mean by linear model isn't the fact that I'm using a line. Linear model means that my parameters that I have is a linear function of parameters. Okay. So I could actually fit a quadratic if I wanted to. But let me show you what this looks like in GeoGebra so we can see the pieces. Okay. All right. Sure. I'm not sure why I did that. There we go. While you're, oops, not settings. Spreadsheet. Oops. All I'm doing right now is just copying and pasting over into Excel, or not Excel, over in GeoGebra, so that I can show you what the whole thing looks like. So the first thing I did in GeoGebra was just literally have those points in there, the X's and the Y's. The reason why I typed that in there first is so that if I create a list of points, if I go over to the graphics menu, you can see the points here. Oops. Right? That was why I did that first. Okay. Just so I can show you what that looks like. Okay. We could solve this in GeoGebra the same way. You can, from a list of things, I'm not going to do it here because I don't want to take the time. But if I do the same thing and highlight it, I can also create a matrix. So if you type in those coefficients like we had in Excel, I can create a matrix, and then I can do the transpose of that matrix and do all the multiplications in GeoGebra as well. Okay. Remember that at the very, very end, what we got was the equation. What was it? It was 5.33, negative 5.33, plus 0.9 times x. And there we can see the line in there. I just wanted to put it in GeoGebra so you could see what the line looked like. You could also do it in Excel. If you create a scatter plot in Excel, you can click on the graph and then tell it to add a trend line. And then it'll also tell you what the coefficients are. You would get the same answer. So Excel will do it too. All right. I do want to do one more example. Notice in this case we did what I said was we were trying to find a least squares line. There's nothing special about doing a line. We just need to make sure that the thing that we're trying to fit is a linear model. But when we may say linear model, we mean linear in the parameters. Okay. So just to do another example here, let me just open up a new sheet. Let's say that instead of doing a linear model, I wanted to do a quadratic model. Okay. So in that case, if I write on the board here real quickly, what I mean is that you're trying to do something like an a plus a bx plus a cx squared. That would be a quadratic model. Again, I can't emphasize this enough. Linear model does not mean a line. Okay, linear model means when I'm looking at my parameters, those are raised to the first power, not multiplied by each other. It's linear in the parameters. That's what linear model means. Okay, I can do whatever I want to the x's. Okay, that's not the linear part. All right. So let's just make up a set of points. Let's say we had, let's do negative 2, 5. Let's do 0, negative 1. Let's say we had 1, negative 1. And let's say we had 3, 8. And let's do one more. Let's say 5 and 13. Lack of a better thing. Okay. So first column is my x's, second column is my y's. Okay. Notice in this case, if I want to set up a system, I've got coefficients for my a, coefficients for my b, and coefficients for my c. Correct? The a's are all going to be 1, right? What's the coefficient on the x's going to be? The x values. What's the coefficients on the c going to be? The x value is squared, right? So if these are my points, if I create my matrix A, my first column will just be all 1s again, right? My second column is just going to be, the x's. So I just said equals A1 and pull it down, right? This one's going to be A1 squared, the squares of all the x's, right? And pull it down. Right? Just plugging it into the function, correct? Okay. All right, what do I want to do with this matrix? First, transpose it. After we transpose it, multiply it by A. So that was our transpose. Here's our A. Notice in this case we get a 3 by 3, which we should, because we have 3 parameters we're trying to solve for. So it'd be a 3 by 3. After we take the A transpose and multiply by the A, we do inverse. It's minverse, I forgot. Okay. Take the matrix inverse of that one. After we take the matrix inverse, we multiply by the transpose. Here's the matrix inverse. Here's the transpose. Right? Finally, I'll do this off to the side so I don't have to scroll down. What do we do next? Yeah, multiply the matrix we just found times the y values. Good, exactly right. So this is where your y values are going to come in. Those are over here, right? Okay. That's it. That's all you have to do. It's the same process every single time. You just have more parameters to solve for. Once you set up your original A matrix, first thing is transpose it, multiply it by the original A, take the inverse of what you got, multiply it by the A transpose, then multiply it by the B. Yeah, Declan.
How do we set up the first matrix?
Which one? The one here or this one?
Yeah.
Okay, so again, we're looking at this model. Your coefficient on your A is every single time is 1. Coefficient on your B is every single time is your X. So I just copied the same X columns over. This is coefficient every time is the square of your X's. So I just did the square of the X's here. So that was where that one came from. Again, just to show you over in GeoGebra real quick, what we have here, I'm going to copy this over. Let's go over to GeoGebra. I'm going to refresh it and add a spreadsheet and create a list of points. And give me an algebra window so I can actually type in the equation. All right, so the equation is we had these values. Get these over here. Okay. Make sure I have the right ones. 0.645. Okay. So the first value is 0.39. Is that right? And it was the second value was that one. It'll be times x. And the next one was a plus. That times x squared. And if I look at my graph, there would be your least squares quadratic. Trying to go through those points as close as possible. So again, the process is the same every single time. So the thing that you have to get set up is the system of the matrix that you need to do. So here's homework for next Thursday. What we have not talked about yet is how to find r squared. We'll talk about that next time. But you should be able to do pretty much everything else. Now, there is an extra step in number 2 because you have to take the model you're trying to fit and convert it to a linear one first. But everything else should be exactly like what we were doing. So next time we will talk about how we calculate the r squared value. The r squared value is a measure of how good your model is. Okay? So we'll go a little bit into how we compute that. Again, we'll do it from a linear algebra perspective just so that we can do the computations. And then as I promised, I'll also show you how to do this in R so you can see what it looks like. All right? Have a good one. We'll see you next week, if not before.